Welcome to the video on the Maclaurin series. So here are some of the most important Maclaurin series expansions. So we have our function e to the x, which is the sum from k equals 0 to infinity of x to the k over k factorial. So when you expand it, it looks like this. You'll have every single term, so your constant, first degree, second degree, third degree, they're all going to be positive. And then your factorial in the denominator will match the degree. For your sine of x, it's the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 over 2k plus 1 factorial. So for this one, you'll have all of your odd degree terms. So you'll have x to the first, third, fifth, seventh, and so on. It'll start with positive, and then the sign will rotate every time from negative to positive, and then your degree will match the factorial in the denominator. For cosine of x, it's the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k over 2k factorial. So for this one, you start with a constant, and you're using all the even degrees. So you have x to the 0, which gives you your constant. Then we have squared to the fourth, to the sixth, and so on. And then your second term will be negative, and the signs are going to rotate from negative to positive, and your degree matches your factorial in the denominator. For your natural log of x plus 1, it'll be the sum from when k equals 0 to infinity of negative 1 to the k times x to the k plus 1 over k plus 1. So you'll start with x. Your degree will increase by 1 every time, and then your degree will match the denominator, but there's no factorial, and then your signs are switching from negative to positive. Finally, you have 1 plus x to the p, where p is an element of the rational numbers, and this is going to be the sum from k equals 0 to infinity of negative 1 to the k times p minus 1, all the way until p minus k plus 1, times x to the k over k factorial, and how it will expand depends on what your p-value is. For Maclaurin series derivations, you'll use substitution to find a Maclaurin series of a known function such as e to the x, the sine of x, cosine of x, etc., with a function g of x in place of x. To do this, you'll simply plug in g of x into the original expansion. So your sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So if you wanted to know your sine of x squared, that would be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial plus x squared to the 7th over 7 factorial, and so on. So you just go ahead and plug whatever is in place of your x into that area there. For products, to find a Maclaurin series of a known function with a function p of x times that function, you'll multiply p of x times the original expansion. So if we had 2 sine of x, that would equal 2 times your sine of x expansion. So times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. For integration, to take the integral of a complicated function, you'll substitute a Maclaurin series for the function to make the integral an integral of a simple polynomial. So if you have a combination of polynomials and trig functions or exponentials or anything that's more complicated, you can switch your complicated function for your Maclaurin series approximation and use that to simplify the function before taking the integral. For differentiation, it's basically the same thing as integration with your Maclaurin series. To take the derivative of a complicated function, you'll substitute the Maclaurin series in the function to make the derivative a derivative of a simple polynomial. So you'll do the same kind of substitution of a Maclaurin series, and then instead of taking the integral, you'll take the derivative. So we talked about developing Maclaurin series in a different video. So what it comes down to is if it's not possible to find an explicit solution when given dy dx equals f of x comma y and a y-intercept 0 comma y initial, a Maclaurin series can be developed to estimate y of x. So for your Maclaurin series, your f of x equals the sum from k equals 0 to infinity of your kth derivative evaluated at 0 over k factorial times x to the k. So you would have f of 0 plus your first derivative at 0 times x plus your second derivative at 0 over 2 factorial times x squared plus your third derivative evaluated at 0 over 3 factorial times x cubed, and so on. So here we have our first IB practice question. It says, write the Maclaurin series for 3x squared sine of x cubed. So our Maclaurin series for the sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So your sine is your odd degree ones. So our sine of x cubed would equal x cubed minus x cubed cubed over 3 factorial plus x cubed to the 5th over 5 factorial minus x cubed to the 7th over 7 factorial plus ... So this equals x cubed minus x to the 9th over 3 factorial, because we'd multiply these, plus x to the 15th over 5 factorial minus x to the 21st over 7 factorial. So now if we have 3x squared times that, so 3x squared times the sine of x cubed, that would be 3x squared times x cubed minus x to the 9th over 3 factorial plus x to the 15th over 5 factorial minus x to the 21st over 7 factorial. So you could go ahead and distribute that in to get that 3x squared sine of x cubed equals 3x to the 5th minus 3x to the 11th over 3 factorial, which is 3 times 2 times 1, so 6, plus 3x to the 17th over 5 factorial, which is 5 times 4 times 3 times 2 times 1, so 120, minus 3x to the 23rd over 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, which equals 5,040. So we can simplify these. So our final answer is 3x squared sine of x cubed equals 3x to the 5th minus x to the 11th over 2 plus x to the 17th over 40 minus x to the 23rd over 1,680. So this would be your answer to this question. On the test, they'll most likely tell you how many terms that you need. So here we have our second IB practice question. It says find the derivative of 2e to the x cubed over x squared using Maclaurin series. So our complex function here is our e to the x cubed. So we'll try to write this using a Maclaurin series. So e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. So e to the x cubed will equal 1 plus x cubed plus x cubed squared over 2 factorial plus x cubed cubed over 3 factorial plus x cubed to the 4th over 4 factorial. So this equals 1 plus x cubed plus x to the 6th over 2 factorial, which is 2, plus x to the 9th over 3 factorial, which is 6, plus x to the 12th over 4 factorial, which is 24. So we're finding the derivative of 2 times e to the x cubed, which we said is 1 plus x cubed plus x to the 6th over 2 plus x to the 9th over 6 plus x to the 12th over 24, all over x squared. We can distribute the 2 in the numerator to get d dx of 2 plus 2x cubed plus x to the 6th plus x to the 9th over 3 plus x to the 12th over 12, all over x squared. So we have d dx of 2x to the negative 2 plus 2x plus x to the 4th plus x to the 7th over 3 plus x to the 10th over 12. So when we take the derivative, we get negative 4 x to the negative 3 plus 2 plus 4x cubed plus 7 over 3 x to the 6th plus 10 over 12 x to the 9th, which we can simplify to 5 over 6. So we get our final answer of negative 4 over x cubed plus 2 plus 4x cubed plus 7/3 x to the 6th plus 5 over 6 x to the 9th. So in summary, these are our Maclaurin series that you need to memorize. You can use substitution to find a Maclaurin series of a known function with a function g of x in place of x by simply plugging in g of x for x into the original expansion. For a product, to find the Maclaurin series of a known function with a function p of x times the function, you'll multiply p of x times the original expansion. For integration, to take the integral of a complicated function, you'll substitute a Maclaurin series in for the function to make the integral an integral of a simple polynomial. For differentiation, to take the derivative of a complicated function, you'll substitute a Maclaurin series in for the function to make the derivative a derivative of a simple polynomial. And for a Maclaurin series to be developed to estimate y of x, you use this here for whichever function you're trying to turn into a Maclaurin series. That's all for this video. Thank you for watching.